Okay, let's get started. So today, obviously, is we're going to continue our discussion of MRI. But before I do that, let me go over some course logistics. So obviously, we just have one more week of class after this. So just in terms of homework assignments, so all the programming assignments are available now. So there's three assignments that are sort of the standard assignment, and then there's one that's for extra credit, so that's optional. Relatively small assignment. I was just telling the people in class here that assignment's a little different from the other ones in that the MATLAB solution is actually very short, and by very short I mean it could be as short as one line. Okay, so the main work on that is actually going back to your first year calculus and just remembering how to take the derivative of an exponential, which everyone should be able to do. So that's really just, once you do that and check your answer, then the MATLAB just helps you check your answer. So that's sort of meant to be an extra credit problem, but it will be related to some of the stuff we talk about today. We are trying to obviously, with sort of, adapting to the current situation, realizing that we want to sort of acknowledge that it is a bit stressful and not having the TAs and the grading. So we're just trying to strike a balance between giving you enough so you cover some material, but also making sure you have time to do your project and everything like that. Okay. So, so some of the homework I might have assigned last year that I did assign last year, I'll be posting it so it's available. So you want to look and see what people did last year, especially with parallel imaging and sort of linear algebraic point of view. We'll go over that material on Monday, but there'll be no formal assignment on that. That's more for those of you who want to sort of do more self-study. We will make those problems are actually already online. If you look under the modules, there's actually a supplementary module for project one, and that's where I typically put extra material. So there's actually quite a few background chapters on different topics and some MATLAB code and things that I put for different groups so that they can use it. And as you're working on your project and you have questions, if I think of a sort of a supplementary material, that's where I will put it for you. Okay. So speaking of projects, so thank you everyone. All the projects have been submitted. So we're all good to go. So that's great. All the projects have been approved. Just note that I did approve projects, but in some cases I said, it seems like it's missing this component, or, think about this. So just take that feedback seriously, because that is only meant to help you improve your score, especially on the difficulty side. I think everyone should be fine on relationship to course content this time. So I think we're all good on that. And especially if you are the only one who sent me the email, then make sure you share my comments with the rest of your group, just so everyone is aware that that's the feedback that was given, so that you all have a sense as a group that, if I did say, well, this is good, but maybe think about this some more, that the whole group can sort of take that into account. All right. So are there any questions about either the homeworks or the project? Yes.
Are there office hours next week?
Yes, there will be office hours. My office hours, the regular office hours after lecture, and then I will post a survey to offer additional office hours. I think last time I said that I was thinking of offering evening office hours, simply because then that won't conflict with any classes, but it seemed like that was okay. But does anyone have a strong objection to that? Especially you're here, so you get more of a say. So anyone online or in class, do you guys prefer 9 to 5 office hours, in which case it's hard to sort of find a time that doesn't conflict with classes, or is evening okay? Any thoughts? Doesn't matter. Okay, so I can just post some times and we'll just do a survey, and I'll probably offer 2 or 3 hours of extra office hours for both the homework assignments and the projects. And obviously on the TA side, you would have to communicate with them independently on what their office hours are. Okay. Any other questions? And then in terms of pre-lecture quizzes, I think there will be at least one more pre-lecture quiz, and then that should be the last one. Okay, so there'll be one based on material from today, and so then after you're done with that, then there's just the finishing up the homework and then working on your projects. Okay, and then I'm not sure, I haven't had a chance to check whether Professor McVeigh has posted the project 2 scores or not. If not, I'll make sure he gets those posted by Monday. And so on Monday, I'll go over sort of the results of those project scores, just so that can give you some added guidance as you're thinking about project 1, where to focus, especially if the score you got for project 1 was not as much as you wanted. There are very clear general trends on what projects scored well and what did not. So I'll go over that. All right. Okay. Any questions about where we are with MRI or anything else course related? Okay. If not, let's start off with just sort of reviewing a little bit. Okay. Evening, please, from one person online. Okay. So most people did fairly well on the pre-lecture quiz. The only question that really stood out was this Gibbs artifact one, which is like, if you see Gibbs artifact, and so just a reminder, Gibbs artifact is this sort of ringing effect that you see. And the question is, what should you do? Okay. And remember, the Gibbs artifact comes about from, how we window in K-space. Okay. So we have a fairly narrow window in K-space, then the Fourier transform of that is going to be, related to a sinc function. Okay. And so, for example, this sinc function that gets convolved with its edge and gives us this ringing, right? So one way of reducing Gibbs artifact is if I make that bigger, okay, then the Fourier transform should get narrower, okay? Because the more data I collect in the wider I go in one domain, the narrower I'll get in the other domain. So one way of dealing with Gibbs artifact is just going out to higher spatial frequencies. All right. So that was sort of the most correct answer given your choices. Okay. I threw in Ram-Lack filter, but that would just amplify the high frequencies and it would sort of destroy your image in other ways. And it's not really clear how you would apply that. Changing the delta K would change your FOV and stuff. So it might have an effect, but it's not clear what the effect would be. Okay, so the most correct answer there is go out farther in K-space such that your sinc gets narrower. All right, so any questions on that? Okay. The other problems, most people did well on, but we'll just review very quickly. So the one involving slice selection, you just have to remember this. If you want to keep the bandwidth the same, then if one thing goes up by, say, a factor of 2 or a factor of 4 or a factor of 8, then the other variable obviously has to go down by that same factor. So that was all you had to apply for that one question. Okay. So today, and then the relaxation questions we'll go over in a minute. So any concerns about those questions that we just went over? Okay, so today we're going to go over relaxation, gradient, and spin echoes. We'll start talking about how you create image contrast, and this will be related to that extra credit problem that you have. And then we'll spend some time sort of doing functional MRI, which is the first real application we're going to do of MRI to something that's not just sort of standard MRI. Okay, so just to remind you, we looked at both T1 and T2 as a function of tumbling rate. Okay. And so we noticed that for T1, the minimum relaxation time occurs when the tumbling rate is at the same frequency as our Larmor frequency. Okay. So as we increase the Larmor frequency going out in this way, you notice there's less stuff that has that tumbling rate. So therefore, the T1 is going to get longer. And so that was one of the questions was, T1 gets longer because why? And one reason is because the Larmor frequency increases with B0. Okay, so that was the main reason that T1 is affected by magnetic field strength. All right, so it's really that Larmor frequency goes into regime where essentially in the limit you go way out to here where there's almost nothing at that frequency, in which case you expect your T1 to get even longer. All right. And then the T2, I think most people got that. Essentially, it's really related to how fast the spins are tumbling. If they're tumbling very fast, the motion averages out. So that's called motional averaging. And so the net effect is very small. So you get very long T2s. And when the relaxation or tumbling rate is very slow, then the effect of each spin on all the other spins is much greater because there's no averaging of the effect. And so spins can dephase much more quickly and T2s are short. And in the for our applications, these T2s occur for things like fat, bone, tendon, cartilage. Okay, so unfortunately, these are a lot of things that you would like to see, especially for orthopedics or musculoskeletal imaging. And so next Friday, there'll be an optional lecture that will go into ultra short echo time imaging, which will sort of talk about one technique that UCSD has really pioneered for looking at things with very short T2s. Okay. This is just to remind you that there are different T1s and T2s. So now we're going to talk about another source of relaxation that we haven't talked about before. And this is one that's actually, it's a little different from the others in that it's really something that actually can be controlled to a certain extent and also corrected for. Okay. And here's the idea. If you, when you buy a magnet, you pay the manufacturer a lot of money for a magnet that ideally is uniform. Okay, so if you have the magnet and then you put, you measure the field at different points in the magnet, it's as uniform as possible. And in fact, what they do is there's a process called shimming where they actually put in little pieces of metal to shim it to get it just right. So there'll be an MRI engineer who comes out and puts in these little pieces of metal just to get the field just right. So it's as uniform as possible. And when you buy a magnet, you're sort of guaranteed a certain uniformity over some sphere, let's say a 30-centimeter sphere, where the field should be fairly uniform. Okay. Because remember, the reconstruction depends on things being uniform, right? You want a uniform B naught, and then on top of that, you put on these linear gradients. So if things are not uniform, then your assumptions are going to be violated and your image will look weird. Okay. But here's the catch. You can spend as much money as you want getting this field as uniform as possible. And then you put a human in, and all of a sudden the field is non-uniform again. Okay. So that's what we want to talk about. So why does that happen? Well, it's because most things that you want to image have magnetic properties. Okay. And so if you imagine this is a uniform magnetic field, and then if you put in something like tissue, which is diamagnetic, it will tend to repulse the field. Okay. So if you go back to freshman physics, you sort of have different permeabilities of different magnetic permeabilities. And so certain things will create magnetic fields that are in opposition to the applied field. And so you can sort of see here, the field lines are pushed away. And you have a field that's sort of opposite of what's applied. And then you have things that are ferromagnetic, especially, things like oxygen, which we'll get to later, because that's the basis of fMRI, and iron, which is also another key basis of fMRI. And these things obviously will tend to concentrate the field. Okay, so you have areas of the brain or the body that tend to concentrate the field, and others that tend to expand or distort the field. So there's going to be some distortion of the field either way. So when you actually go and look at the magnetic field in an object, it will be non-uniform, no matter how uniform your object started off, your applied field was. So that's related to magnetic susceptibility or permeability, sort of related concepts there. So here's an example. So this is axial views of someone's brain. Okay, so these images look pretty good. So these are just showing you sort of essentially like the proton density, where these are probably T1 weighted because the CSF is a little dark here. So in any case, there's some sort of, obviously there's some sort of brain here. Okay. So this is just showing you the gross anatomy of the brain. And here what we're plotting is the fields. And so dark means the fields are weaker and bright means the fields are stronger. And then here it's in between. So you can sort of see here at the front of the brain, there's a really big change in the field. Like if I go from here to here, that's a pretty big change in the field. Okay, so that's a huge inhomogeneity. So can anyone sort of think about why would you have such a big inhomogeneity at the front of the head? Like why here? Why not in the back of the head? You see a little bit around here too, on the sides of the head, right? So what's going on on the sides of your head at the front of your head? What do you have? There. Go ahead. You have ears and you have a nose, right? Okay. What else?
You're breathing the air
Okay, so there's air, so air is involved. So what has anyone here, like when you get a cold and you get congested, what gets congested? Yeah, the sinuses, right? So anyone have like a sinus infection or a sinus congestion? Typically, you have these big air pockets here, okay, all over. And so those basically are the main cause of these things. Okay. Sorry, what is the question? There's a question about mouse. Can you expand on what the question is online? And yes, the human body does have diamagnetic fields. Yes. Yes, can you not see the mouse? Okay. Okay, so let's talk a little bit about what happens in the presence of inhomogeneous fields. Let's say we start at the beginning of the experiment and the image I showed was actually of a human head, not a mouse. So hopefully that clarifies that. So at the beginning of the experiment, assume all the spins are the same, okay? And then let's say I put these spins in the presence, like let's say these spins are around this, they're sort of all distributed around here, where the different colors show that they're all in a different magnetic field position. So what's going to happen is, since they're different magnetic field strengths, they're all going to precess slightly at different rates, okay? And so if I come back some later time, TE, which stands for echo time, or time of echo. We'll talk about that later, but for now, it's just we're going to look back at some point in time at these spins. Then if there's some inhomogeneity, there's going to be some dephasing of the spins. Okay. So the net vector sum is going to be decreased. Now imagine that somehow I made the inhomogeneity even stronger. So there's a lot more change in the magnetic field, right? So now if I think about these same spins, right? Now they're in very different magnetic field strengths. And so they're going to get out of dephase even more. And so the more inhomogeneity, more dephasing, that's even a more decrease in the magnetic field. Okay, so it tends to be where you're in very inhomogeneous areas. In some cases, it can be so bad that by the time you look at your image, there's no signal because everything is dephased. Okay. So that's sort of the signal decay that we're talking about. So the way we talk about that is signal inhomogeneities. And the only thing here is, I'm going to point out is here, previously we talked about a T2 term. So we had e to the minus t over t2. And that's just due to the random tumbling of spins. Today, we're going to introduce a new additional term, T2 prime. And that's related to the static inhomogeneities. Okay. So what we end up with is, and furthermore, we're going to define something called T2 star. Okay, and the relationship is 1 over T2 star equals 1 over T2 plus 1 over T2 prime. You might also see this written as R2 star equals R2 plus R2 prime, where this is just 1 over T2 star. This is just 1 over T2. This is 1 over T2 prime. This form is a little sort of more intuitive, especially if you come from like chemical kinetics, right? It's just the rate, the overall rate is just the addition of the two rates. Okay. So just to remind you, this term is what we've talked about. It's due to the random motion of spins, and it's not reversible. At least no one has figured out how to reverse it yet, because it's just random. Okay. This part actually is due to static inhomogeneities. So it turns out it is reversible. And one way to do it is with a spin echo sequence, which we'll talk about soon. Okay. So let's just do a little bit of terminology. So T2 star decay, T2 star refers to when we have both the T2 and the T2 prime. So we have both the random and the static inhomogeneities contributing to our decay. And typically, that's going to be sort of what we refer to as a gradient echo sequence. Okay. The gradient echo simply means that we refocus the spins with the gradients, and it typically refers to the refocusing of the spins at kx equals 0. Okay, so that's the part of the refocusing. So if everything was perfect and there was no inhomogeneities, everything, once the gradient gets back to kx equals 0, especially if you're at kx equals 0, ky equals 0, then all the spins should be phased again, okay? So for example, if you thought about this readout gradient, this initial gradient takes you out in k space, so it dephases the spins, gets them out of line, but then you come back across k space, and so by this time, when you cross this point in k space, you should be at kx equals 0, right? And kx equals 0 just means along any row that you're going to see the same spins along. So if that were the case, and my object, let's say my object was a rect function, right? Then the Fourier transform would be a sinc function. So if there was no decay, I should just see a sinc function. Okay, but since there is decay and there's exponential decay, the sigmoid measure is actually going to be decaying with this exponential decay. And at the echo time, it has weighting, the center of k space is weighted exp minus te over t2 star. So it turns out that when we start talking about different image contrasts and how things are weighted, we typically are going to look at the weighting at center of k space, kx equals 0. Okay. Because remember, the center of k space is sort of the overall average of your image. So that's sort of the overall weighting that you care about. What is the weighting at the center of k space? So here's some susceptibility artifacts. So here, there's some big divots in this person's femur. And here, this person doesn't look like they have a mouth. Okay, so what's going on? Does this person have a mouth or not? What do you think is going on with this person here? What could be, I mean, this is not good, right? So so online, one guess is braces, right? Okay. So braces, anything metallic could perturb the magnetic fields, right? And so yes, this person has dental work. And that actually is one of the things before we scan someone, we have to ask, do you have dental work? Not necessarily because it's a safety concern, which it could be, if you have a lot of braces, the RF energy can actually heat up your braces and you could get a burn in your mouth if the wrong sequence is used. But it's also because it just means that we know that the images are going to look horrible. Okay. What about this person? Does actually person have holes in their femur, or what do you think is going on with this person? What do you think these are due to? Yeah, they probably have screws, right? They've had surgery, right? So there's something there that's perturbing the fields. So it's probably safe. It's still probably MRI. Obviously, it was MRI safe because they scanned these people, and they hopefully they were okay. But it's just more that the image quality. So actually, I don't think actually one group might look at it. One area of study and research is, obviously in the clinical environment, like if, the probability of you scanning someone who has, if you're scanning sick people, I mean, they're in the hospital because they're sick. So they will tend to be older and have had maybe surgeries. And so these are actually metallic implants actually become a big concern, is how do you get good images even among people who have metallic implants? Okay, so that is actually something that people work on. There may be a group that touches upon that in one of their in the artifacts presentation, but we'll see. Okay, so obviously you'd like to be able to image and get rid of this, right? So one approach that was invented, in 1950s, a long time ago, is something called the spin echo, and it's one of the key concepts in MRI. It was actually invented in NMR before there was even MRI, but later on people realized, oh, this is really useful for MRI as well. Okay, so here's the idea: you have these spins, and let's say over time they dephase, and so here are the spins who have dephased, right? And so notice this red spin, he's gone. Whoops, sorry. He's gone counterclockwise, right? and this green spin has gone clockwise, right? So the green spin is processing faster, right? And the red spin is processing slower. Right? So it's almost as if you had a race and you had people start off at the same time. And let's say you checked in on them a minute later. Someone's at the front and someone's at the back, right? So at 1 minute time, you take the person in the front and you move them to the back. You take the person at the back and you move them to the front. And then you wait another minute. And what should you see after that additional minute? Assuming they keep going the same rate. Yeah, they're all going to be grouped together then, right? Because the person who you put in the back, the fast person who you put to the back is now going to catch up. And the slow person who you put in the front is going to slow down. And so they're all going to meet again. So that's the idea behind the spin echo. Okay, so you find a way, and this is done with using what's the 180-degree RF pulse. So essentially you flip. So imagine these are your spins here, and they dephase, right? And so this person is slow, this spin is slow, this spin is fast. Now you apply a pulse that flips them 180 degrees. Can't really turn all the way. You do more yoga, like this. And so now this is the fast and the slow spin, and then over time they recoalesce. Okay. So that's the idea behind spin echo. And so magically, if you wait echo time over 2, then at echo time, all the spins have rephased. So that's pretty cool, right? So spin echo is a real bread and butter sequence. I think one of the projects is going to look at fast spin echo, which is a variant of spin echo. So this is a movie that sort of gives you the same idea. So you sort of see the spins dephasing. There's a pancake flipped, and then they rephase. So once again, we let them dephase, we flip them, and then they rephase. Okay. So it means there's typically an excitation pulse, there's a 180-degree refocusing pulse, and then there's a time where we look at the spins. Okay. So this is what's called a spin echo pulse sequence. So essentially, we have a 90-degree pulse, we have our slice selection pulse and refocusing pulse we talked about. Here's our spin warp gradients. And now we apply this 180-degree pulse that does the flipping. Okay. And notice here, the readout gradient is actually the same sign. Typically, before we had something that looked like this, right? Because of that flipping, it turns out that we need to keep these the same sign. And if we look at the amplitude, the blue here is the ideal signal we would get, a sync pulse, if we had gotten our object had been a rect function, and now we have this e to the minus t over t2 decay here. That's the part that's just due to t2, and then this additional decay here is due to the t2 prime. But notice at this point, it's been refocused, and so there is no effect there. So essentially, we reduce this additional t2 prime effect by doing that refocusing. So this is an example of what that can do. So this is just a uniform sphere, and they probably introduced some gradients. They turn on the gradient or somehow to induce some nonlinearities. And so you can sort of see here, these dark areas are areas where the fields are changing so fast that the spins dephase. Okay, so if I did a gradient echo image, these would be the bands in my image. All right. Now, all I do is I add that 180-degree refocusing pulse. Now I have a nice spin echo image. Okay, so just to remind you, so we have T2 decay, and then additional T2 star decay when we add the T2 prime component. Okay. And if we can do a spin echo, then we can go from this decay curve back to this decay curve. Okay. What that means is, for example, at this point in time, if I have a spin echo, I actually still have some signal, whereas if I have a gradient echo, all the signal would be almost gone. All right. Okay, so now we talked about T1, T2, and T2 star. And also, so different tissues have different T1, T2, and T2 star. And also different tissues can have different proton densities. And so we want to take advantage of that diversity to adjust our pulse sequence that we can create contrast between tissues. Okay. And there's lots of ways of doing that. Today, we're just going to cover mostly echo time and repetition time. So those are two of the most fundamental things that we can adjust to create different image contrast. And so let's go over what these are. So this is what's called a saturation recovery sequence, which just means that we flip the spins with a 90-degree pulse, then we acquire the data, and then we wait some time, and then we'll flip the spins again with another 90-degree pulse. We wait some time, echo time, acquire the data, and then we flip again. So the time between the 90-degree pulses is TR, which stands for repetition time, or time of repetition. Okay. And then this echo time, TE, is where we cross KX equals 0. All right. And so saturation recovery, because we have this term here. Okay. So at time equals 0, right after this pulse, we're starting off at 0 m sub z, right? And then we're saturating. It's a recovery from saturation. So this is saturation. Okay, so after the 90. The 90 flips everything down to transverse, so there's m sub z 0. So that the m sub z component is, so this is representing the m sub z component, right? Recovery. All right, so in every location where we have a T1, there's some T1 recovery. Okay, and that's the m sub z recover. This is the transverse decay, right? This term is saying things are going to decay in my transverse plane with some T2 star decay, because that's the dephasing of those spins. And this is just the density. How many spins do I have at that location? Right? So my image is going to depend on those three factors. And so we're going to play around and say, and the things we're going to play around with are TR and TE. Right, because those are the only things that we can control, because the proton density, at least for now, we're going to assume is not up to us. Now, we could introduce contrast agents later, but for now, we're going to assume we're just trying to image the object. And then every object will have a TR and a sort of a T1 and a T2 star. That will either be the native T1 and T2 star of our object, or later on, I don't think there's any projects on contrast agents, but in some cases, especially in clinical cases, we will inject contrast agents to modify the T1 and T2 star. But for now, we're just going to assume it's just the tissue T1 and T2 star. Okay, and then sorry, this is overlapping, but this is just showing that if it's a spin echo sequence, then we just add that additional 180-degree pulse. Okay, so let's talk about a T1 weighted sequence. So the key with the T1 weighted sequence, we want to make TE very short compared to either T2 or T2 star, such that the e to the minus TE over T2 star goes to 1. Okay, so we can ignore it. So now you look and see our image intensity just depends on the proton density and the saturation recovery that depends on T1. All right. So the principle behind T1 contrast is here. If I have a tissue that has a very short T1, then its longitudinal magnetization recovers quite quickly. So the next time I flip it over, I have more magnetization to deal with in my image. Okay? So there'll be a stronger intensity. Here, I have a very long T1. So wait the same amount of time, there's not as much signal. So when I flip it over, there's less signal. Okay? So I'd expect that tissue to look darker because there's less signal. This is the part that's related to your extra credit problem. So here, you are, in this case, we're assuming that there's two tissues, one with T1 of 800 and one with 1200. Okay, so let's call this tissue A and tissue B. And for this one, we're assuming the densities are the same too. Okay, so for the extra credit problem, your inputs are going to be your rho sub A, your rho sub B, and these T1s. Okay, and so if you look at these, obviously the one with the shorter T1, you see it recovering, starts at 0 and it recovers faster than the one with a longer T1. And then this is the difference of those two signals. And you can sort of see the difference of two exponentials tends to have this shape, okay, assuming that this is bigger than this. And so this is the difference signal. Delta M is equal to, so say, the M sub A signal minus the M sub B signal. Okay, and you can sort of see there's some maximum here, which if we zoom in is, it's close to 1,000, not quite 1,000, right? So in fact, the first test case on your extra credit is assume that rho A equals rho B, and I think I set those equal to 1. Assume these T1s, 800 and 1200. You are supposed to write a function that finds the TR that maximizes this signal. Okay? And so you can sort of always check it because this is the answer essentially here. Your answer needs to be pretty close to 1,000 if your code is right. Okay, so that's the first sanity. If you do that extra credit problem, which is optional, that's the first sanity check is if you plug in these values, you better get something close to 1,000. Okay, and obviously the MATLAB will check for you, so it'll check exactly whether you get the right answer. Okay, so a good rule of thumb is given any two T1s, so this is 800, 1200, and assuming the proton densities are the same, then if you look at the maximum here, it's about 1,000. So it's sort of the average of these two, right? The average of 800, 1200 is 1,000. So if you're just trying to make a guess, like let's say you don't have a calculator, you're at the console, you're trying to maximize things. Sometimes you just have to make your best guess under time pressure. So this is not a bad guess, right? If you had to pick a TR, just pick it as the average of the T1s you're trying to differentiate. Now, you may be wrong because the proton densities also come into play, but as a good first guess, it's not a bad first guess. Okay. So that's T1 weighted scans. T1 weighted scans, one area that sort of is pretty obvious where T1 weighted scans, it's pretty clear what the T1 effect is any time you have something where there's a lot of fat, and in this case, this person has a lot of fat in their brain, which shouldn't, in a healthy person, you wouldn't see that much fat. And so remember, fats have a very low tumbling rate, and so the T1 is very short. So if I have a T1 weighted sequence, anything with a very short T1 is going to be very bright. So if you were looking for, hey, I know this person has a history of fatty lesions, then a T1 weighted sequence would show that. Okay. The next thing we might want to say is actually, I want to actually care about T2. I think that the thing that's clinical relevance is tissues have different T2s. Okay. So if that's the case, then I want to make TR very long compared to T1, right? So then in that case, 1 minus EXP minus TR over T1 is going to go to 1, right? Because this term is going to go to 0, right? So basically, all that means is I wait long enough so that no matter what the T1 is, things have recovered. So I have the full M sub Z magnetization to work with. And in that case, I'm just left with the proton density and this T2 or e to the minus TE over T2 star. Okay, so this is if I did a spin echo, and this is if I did a gradient echo. So let's look at this. So you can play the same game. There's two tissues here, and there's not going to be a homework assignment on this, so don't worry about this, but it's the same principle as the other one. It's just, if you did the other one, you also get a similar solution for this one. In fact, the same formula would apply because they're both difference of exponentials, right? So here we have one tissue and here again, we're assuming this is tissue A, tissue B, and here we can assume that we're assuming rho A equals rho B equals 1 because they're both starting at the same value. So we're assuming they're both starting with the same density, and now they're just decaying. So this one decays with a time constant of 120. This decays faster with a time constant of 80. And this is the difference signal, delta M equals MA, or in this case, it's MB minus MA. Okay. And so this is a different signal. You can sort of see it's maxing out close to 100, right? And once again, a good rule of thumb is, well, 100 is about the average of these two. So I know that two things have comparable proton densities, then I know that the difference is going to be maximized when echo time is close to the average of those T2s. So here's a case where, remember, fluids have really long T2s, okay? Because in a fluid, the spins are very mobile, right? So there's a lot of motional averaging. And so the net effect of any one spin on any other spin sort of averages out, okay? So there's very little dephasing and very long T2s. So that means anywhere you have a lot of fluid in the brain, you're gonna have, if it's T2 weighted, those tissues have a long T2, so they're not going to decay very fast, right? That e to the minus TE over T2, that term is going to be still close to 1. So if you look at a normal subject with a T2 weighted scan, the bright areas are here. These are in your ventricles, okay? So these are spaces in the brain that are filled with cerebral spinal fluid, okay? And these sort of have two purposes. They're part of the nutrition of the brain, but they're also, it's turning out, they're a really important part of getting rid of waste products in the brain. In fact, over the last 5 years, there's been a lot of talk about whether this is somehow related to like Alzheimer's disease and neurodegenerative diseases, where this flushing typically goes on mostly when you're sleeping, okay? And so older people don't sleep as well. So one thought is they don't have this flushing of the brain, and so the CSF can't flush out the waste products. And so that leads to more damage of the brain. And maybe that's why, one reason why, people end up with Alzheimer's or other dementias, okay? The other problem that can happen is anytime you have injury to the brain, there's this thing called edema where the brain will tend to, as it's trying to heal, it'll try to bring a lot of fluid to that area. One reason to bring fluid, obviously, you don't want to wash out waste products and things like that. So more fluid is a response. And so a lot of times, when you injure yourself, you feel a lot of swelling of an area, right? So there's a lot of fluid accumulation, right? And so in this case here, this is just showing that they have a lot of fluid. And so oftentimes, like if there's a tumor, it might be surrounded by a lot of fluid, or any other injury. So this T2 weighted tends to be used a lot if you want to see how much fluid there is in someone's brain. Okay, and the other thing you can do is you can say, well, actually, I care about the proton density. I just care about the density of protons in the brain. So in this case, I'm going to make TR very long, and I'm going to use a very short T. And the limit, TR would go to infinity, and TE would go to 0. Okay, so that's in the limit. Now, obviously, in practice, you don't want to make TR go to infinity, because then you have to wait forever. So you just make TR long. And so in that case, the image intensity is just related to the proton density. So one example of that would be, this is a subject with a form of multiple sclerosis. And here they're looking at areas in the white matter and just sort of seeing a change in the proton density image in this subject. And so what they notice is that in these patients with multiple sclerosis, there tended to be a change in the proton density here in the white matter regions here. So all these dark areas here are white matter. The white matter tends to have less water. And so here, this is typical white matter, and here I think they're seeing an enhancement of proton density here around this area. Okay, so any questions before we have you guys do a little exercise? Okay, so this is how we're going to do this exercise. These are 3 images of the same brain. Okay, this is the same person lying in the scanner, and all we did was we acquired 3 different images. So we acquired a T1 weighted image, a density weighted image, and a T2 weighted image. Okay, these are the relative proton densities of cerebral spinal fluid, gray matter, and white matter. Just to tell you what those are, cerebral spinal fluid is typically in these ventricles here, these dark areas. And it's also all the fluid bathing your brain around here. Okay, so everything that's dark here is cerebral spinal fluid. Everything that's really bright here is cerebral spinal fluid. Okay, so that's where the CSF is. Gray matter is the neurons in your brain. And so if you look here, it's hard to see, but it's sort of the gray area that's sort of surrounding all these folds. Okay, that's your gray matter. And here it's much easier to see. The gray matter is all this white stuff because there's a lot of density there. And here it's a little hard to see, but it's just harder to see here because it's mostly CSF you see. Okay, the white matter is actually the most prominent thing here. So here it looks whiter. And so here, this is all the wiring in your brain. Okay. So you notice you have, a lot of your brain is not, I mean, you have neurons doing a lot of stuff, but a lot of your brain is just wiring, okay, to hook up the different parts of your brain. And so here it's very white, here it's relatively dark, and here it's even darker yet. So I would like you to just take a guess at what would be reasonable values of TR and TE to achieve T1 weighted, density weighted, and T2 weighted images. So the way we're going to do this is in class, we'll sort of do an audio poll. For each one, we'll just ask you to shout out what you think TR and TE should be. And then online, if you could enter in the chat, sort of your guess. You can direct message to everyone or just to me, whatever you're comfortable with. And just, the names could be, for T1 weighted, you just say the TR and TE. For B and C. So it could be in this format or just anything that sort of gets your point across. Let's just take maybe 4 minutes to do this. So go ahead and look at this. Feel free to discuss this with your neighbors or online. You can chat with someone directly or to the group. And then we'll reconvene in a few minutes, okay? Here. Okay, so let's take a look at this. So in class, so let's look at the T1 weighted image first, okay? So if everyone can just yell out, what do you think, what would be like the optimal echo time if you could do it? So just at the count of 3, just yell out what you think would be the right answer. 1, 2, 3. Okay, 2,500. Anybody else? Any other offers? Okay, remember for a T1 weighted image, we want to get rid of T2 dependence, right? So how do I make e to the minus TE over T2 go away? 0, right? So actually I want TE to go to 0 or as small as possible, okay? All right, what about TR? So at the count of 3, just yell out your best guess for TR. 1, 2, 3. 2,000. Okay. Okay. Any other offers? So we have it at 2,000. Okay, to the man back there with the hat. Okay, $2,000, right? Okay. So let's think about that. So let's look at the T1. So we've got 850, 1350, and 4,000, right? So 2,000 would sort of distinguish between gray and CSF, but it's not really going to help me distinguish between gray and white, right? So the idea is here, I have 2 things that are fairly close together and this one guy who's way out there. Okay, so what I actually want to do is probably pick the average of these 2 guys because I want to distinguish these 2. This one's going to be dark. If I pick something here, this one's going to end up dark anyways because it's such a long T1, right? So it doesn't really matter if I pick 1,000 or 800, it's going to be dark, which is good. And so I really want to distinguish these 2. So in this case, I want to pick TR closer to, what is that? 1,100 maybe? Okay, whatever the average of 850 and 1350 is. Okay, so those are 500, so about 1,100, right? Okay, so that would be my first guess. If I was at the scanner and I was trying to do this, this would be my first guess. Now, it wouldn't be quite 1,100 because think about the proton densities are actually slightly different. Right. So in this case, if I actually have this, I would actually take the MATLAB program you're writing and I would plug in these numbers and that would actually give me the TR. Okay. So that might be something. Once you have the MATLAB program running, just plug in these values and see what you get for your TR. Okay. All right. Let's look at density weighted. Okay. For density weighted, what should the TE be? So at the count of 3, 1, 2, 3, 0, right? And what about TR? How long should I make TR? 1, 2, 3. What is that? 5 what? 5,000. Okay. 5,000. Okay, so 5,000. So 5,000 is not a bad guess, but it's sort of close to 4,000, right? So that's still going to be recovering, right? So if I really wanted to sort of cover myself, I'd probably pick typically for recovering exponential in engineering terms, waiting 3 to 5 time constants is about right. Okay, so in this case, I'd probably wager 3 times 4,000. So probably 12,000. Okay, if I really want to get rid of the T wonder, and I really, really want to get rid of it, I might wait even longer, like 4 or 5 time constants. That's sort of overkill, right? By about 3 or 5 time constants, you're back to 98 or 99%. All right. So probably maybe 12,000. Okay, so let's look at the last one, part C. So let's do the TR first. So the count of 3, what would you pick for the TR for a T2 weighted image? 1, 2, 3. 6,000. Okay, so 6,000 not bad, but we picked 12,000 for proton density, so probably want to just stick with that, right? Because that would get rid of that TR term. And what should we pick for the TE? Okay, count of 3, 1, 2, 3. 100. Okay, yeah, that's about right. Because once again, we're in this case where there's 2 of them with similar T2s and 1 with this T2 that's really long. So no matter if we pick anything close to these, this one is always going to be very bright, right? Because e to the minus that small number over 2,000 is still going to be close to 1. And then the average of these two is about, what is that, 30, 90, 95 or so, right? So 100 is not a bad guess, right? So that's basically, you know, if you sort of understand this picture, then you have a pretty good sense of at least a first order understanding of what's going on when people are picking different TEs and TRs to get different image contrasts. Right? So any questions before we move on from that? Okay. You can't actually choose 0, although with ultra short echo time, you can actually get pretty darn close to 0. But for most clinical scanners that don't have that, typically the minimum echo time might be 3 or 4 milliseconds. Okay, which is good enough for like this stuff, but it's not good enough for like bone or cartilage. Okay, so just gonna say, yep, question. Why is it? Oh, actually, it should be closer to 12,000. So whatever we picked for part B would be also a good answer for part C. So we just want TR long enough such that 1 minus e to the minus TR over T1 goes to 1, right? So typically 3 time constants is pretty good. So 3 times 4,000 is 12,000. So yeah, thanks for clarifying. Okay, any other questions before we move on? Okay, so I'm just going to cover some topics that just for your sort of background knowledge. There is one group that's going to go over this flash sequence in more detail. I'm just going to give you an overview of this. Actually turns to be a very popular sequence. I don't know the exact story, but I believe the person who invented this got really rich by inventing this from the patent. So it turns out in MR, if you actually are able to invent something that everyone uses, you can actually make a lot of money. Okay, so here's the idea that instead of a 90-degree pulse, he's using a smaller flip angle. So this will typically be like 20 or 30-degree pulse. And then he makes the TR very short. Okay. And then it turned out that the expression for the intensity looks like this, and that the signal intensity can be maximized at what's called the Ernst angle. Okay. And here's the basic physical principle behind this. It's in remembering the saturation to recovery, I'm using a 90-degree pulse. I'm always recovering from 0. I have to wait for recovery from 0. Okay. So the analogy is like if you use like an old-fashioned like flush toilet, right? And you flush all the water out, right? Then you've got to wait a long time for the water to rebuild before you can get another good flush. Okay. But now, for example, you know, in a lot of places you see these like low flush toilets, right? So it's the same principle. If you only flush half of this much, right, then you don't have to wait as long before you can get a decent next flush, right? So you're sort of giving up sort of the strength of your flush may not be as strong, but you don't have to wait as long between flushes. Okay, that means your TR, the time you wait, can be reduced quite a bit, and so you can go faster. And so typically where this sequence is used, it's used a lot in cardiac imaging where you want to go fast. It's also used what are called localizer scans. When you put the subject into the scanner, you just want a very quick image, scout images, to see where the person is. And these are typically done with a flash-based sequence. Okay, so this is under rapid imaging. Okay, and so here's the idea that this is a T1 of 1,000. Okay, and typically we said before that for this to recover, you might have to wait like on the order of 1,000 milliseconds, right? If you want the signal to recover. Okay. But it turns out that if you use a smaller flip angle, so here in this case, let's say I wanted to repeat my image every 500 milliseconds, and I just chose a small flip angle. So instead of using 90 degrees, I use a 50-degree flip angle. Then I can get half the intensity that I would have gotten with the 90-degree pulse. So it's not as much as I would have gotten if I flip all the magnetization, but the advantage here is I don't have to wait around and I can go very quickly. And I can go even faster. I can go 30 milliseconds. And here, if I pick the right flip angle, then I can get 1/10 of the magnetization I would have gotten with a full 90-degree pulse. With the advantage is I can go super fast. Okay, so that turns out to be a trade-off that we make a lot in MR. Is oftentimes we're willing to give up some signals if we can go faster. The other thing that we see a lot in MR that's a useful thing to know is that previously we talked about this 90-degree pulse, this 180-degree pulse as sort of our spin echo. Oftentimes what we'll do is before we even excite the magnetization, we'll put in what's called an inversion pulse. Okay. And so there, now the equation is we're recovering from minus m naught. So this, we put in this inversion pulse like that, right? So this is the time we put in a 180-degree pulse here. And then here, if we excite with a 90-degree pulse here, when it's crossing 0, that means at that point, this 90-degree pulse has nothing to excite. So that tissue is going to look to be 0 at that point in time. So the intensity is 0 when this inversion time, this TI, satisfies this equation. So it depends on both TR and T1. Okay. And so here's an example of that. So basically what this does is it allows me to sort of essentially erase the contributions of different tissues if I set the inversion time correctly. So for example, here, if I acquire here, I erase the contributions of white matter. Here I erase the contributions of fat. Here I erase the contributions of CSF. Okay. So here we've nulled out fat. Here we've nulled out white matter. Here I've nulled out gray matter, and here I've nulled out CSF. So here see how the CSF, the fluid is all dark. Here you sort of see the neurons are all dark, but the white matter is bright. Here this white matter area is very dark. Okay, so it's pretty cool. I can basically go through and null out different tissues. One area you can do that is, for example, in cardiac imaging. Sometimes you don't want to have to see the blood that's flowing through the chambers. And so you might do something where you null out blood. Okay, so you can just sort of see the tissue and not have to worry about the swirling blood. Okay. So this is an example here. Here we've nulled out CSF, and here it's a black blood. So I've nulled out all the blood that's flowing in the tissue, in the heart. Sorry. Is that a movie? No, it's not. Okay. It turns out I can play a lot of these 180-degree pulses and even try to null out everything that's not flowing. And so in this case, this is an image of an artery that's flowing. And basically I've nulled out all the background tissue. Okay. So inversion pulses turned out to be very useful for sort of erasing parts of the tissue. You're not actually getting rid of the tissue, but you're getting rid of the magnetization component of that tissue. So it's a tool that is used quite a lot. So if you hear about the term inversion prepared, this is what they're talking about. They're using inversion pulses to somehow change the magnetization to get rid of certain tissues and highlight other tissues. Okay. Okay, so before we transition to fMRI, are there any questions about image contrast and things like that? Nothing online. Okay, so we're going to spend the last time in this lecture, and if it goes over to the next lecture, we'll finish up on fMRI. So pretty much everything we've talked about now would apply to if you just really wanted to study brain anatomy. Okay. And what we want to do is start talking about how fMRI, especially over the past, well, I guess 30 years now, has been used to study brain function. Okay, what actually the brain is doing, not just what it looks like. So the fMRI experiment is very much has very things that are common to the just an MRI scan, which is the subject will lie in the scanner. The difference is that you can actually have the subject do things in the scanner. So in this case, they may be playing chess or playing some sort of game. So you might have a screen showing them some display. You could have audio inputs here, and you could have a joystick or some button response box. So you could actually essentially, in some cases, you have them play a video game or like a virtual reality game in the scanner. Okay. So the history of functional MRI, it's relatively recent. It really began with this paper in 1992 by Seiji Ogawa, who sort of first noticed this. And this is from one of the first papers where he's looking at the MRI signal in an area of the brain back here. This is in your visual cortex back here on your head. And this is the area responsible for processing visual information. And so what he noticed in this experiment was that he's shown a light, they're turning on the light at these points in time, and he looked at the MR signal and it went up and down and up and down in response to that light. So this is one of the first demonstrations that you could actually see a functional response in the brain. Okay. And one thing that was interesting is here the echo time is 40 milliseconds. You see the response. If you change the echo time to 8 milliseconds, you don't see much of a response. So this is indicating that there's some relaxation effect going on here. This is actually quite old. This is only about to 2016, but you can sort of see that the number of publications is sort of not quite exponential, but there's just been a lot of work in this area. So now pretty much every major university will be doing some work in fMRI now. Okay. So the major trade-off we make is, an image like this, typically these days in a clinical scan, you might spend about 4 to 6 minutes acquiring a nice high resolution image of the brain, typically at 1 millimeter isotropic resolution. Okay. But the problem is in 4 or 5 minutes, your brain has gone through many states, right? So it's really not a good time scale for studying brain function, right? I mean, you can only probably guess what you were doing 4 or 5 minutes ago, right? Aside from being in this room, you don't actually know exactly what you were thinking, right? So we want to trade off spatial resolution for temporal resolution. So this is, for example, an image of the brain, just one slice in the brain that has lower resolution, maybe, I guess in this case, 3 by 3 by 5. And this slice could be imaged in 60 milliseconds. Okay, so very quickly. It turns out that with current state of the art, we can do current state of the art is about 2 millimeter isotropic resolution. Okay, so 2 by 2 by 2, and we can do it in about 800 milliseconds. Okay, so using the latest technologies and the latest scanners, every second we can get a pretty good image of your brain. Okay, now 2 by 2 by 2 is still 8 times the volume of this, but it's a reasonable time scale for a lot of the work that we want to do. And the key, the bread and butter, is what's called echoplanar imaging, which in past years there's been homework assignment on it. This year we're not going to have time to do that, but essentially it's the zigzag pattern through K-space. So basically, instead of going line by line by line, we just say we're just going to zigzag through K-space. And the key is we need to zigzag. We need to do this. This time of acquisition has to be on the order of T2 star. Basically, we got to get through K-space before things are decayed. Okay, we wait too long, then things will have decayed away. So that means T2 star in the brain, for example, at 3 Tesla, say T2 star is typically on the order of 50 milliseconds. So that means we've got to go through K-space on the order of 50 milliseconds or faster. Okay. So a lot of the work over the last 20 or 30 years is ways of going through K-space faster. Okay, and we'll get a little bit to that on Monday when we talk about parallel imaging, which is one of the ways you can go through K-space faster. Okay, so just to remind you, what is fMRI? Anatomy is high resolution but relatively slow. In fMRI, we go for lower resolution, but go faster. And so, for example, and then we acquire a bunch of images over time. And so, and then while we're doing that, we typically might have some stimulus. So here we might show a pattern during where this is high, and then during these off periods, we're showing a blank screen, and then we acquire the data as that stimulus is happening. And then if we look at some voxel or region of the brain, what we typically see is the signal goes up and down in response to that stimulus. And then fMRI involves, there's a lot of statistics behind it, because now we're sort of looking at time signals as a function of space and time. And so in this case, we might correlate this signal with this signal. And here we just calculate the correlation coefficient between these two signals, and we can plot it. And here we just thresholded anything with the correlation coefficient over 0.6 we're showing. Everything else is not shown. And so just showing here that the areas that have the highest correlation are back here in the back of the brain, which is what you expect, because that's the visual cortex. Okay, and so here is someone tapping their fingers. So can you tell, based on, anyone want to guess, are they tapping the fingers on the right hand or the left hand? Right. Yeah, the right hand, because the fibers cross over, right? Okay. So let's talk a little bit about bold contrast. So we already showed this slide here. So we know there's an echo time dependence. So it must be that, and it seems like the contrast depends on how long we wait to acquire the signal. And so reminder, it's got probably related to this related to R2 star, which was, remember, R2 star is just 1 over T2 star. And so it turns out it's primarily related to this dephasing of the spins, this T2 prime component. Okay. There is a T2 component, but by far the biggest contribution is going to be this T2 prime component. So let's look at that. So this is exactly the same thing I showed you before. Okay. And that's that principle of, if there's more inhomogeneities, there's going to be more dephasing and the signal is going to decay faster. If there's less inhomogeneity, there's less dephasing and the signal doesn't decay as fast. So we're weighting this amount from 0 to echo time to see how much the dephasing of the signal is and how big that signal is going to be. So then the question is, so the idea is, during some baseline condition, we have decay with some R2 star. And then when the brain's active, we tend to have a slower decay. Okay. And then the bold signal, which stands for blood oxygenation level dependent signal, is sort of, we typically take the difference of these two signals and divide by the baseline signal. So this is sort of a percent change that we're looking at. Okay, so we're essentially looking at this percent change. Okay, and it turns out that that percent change is proportional to the echo time times the delta R2 star. Okay. And so this starts giving us some insight into, obviously we need to make this echo time non-zero, and the bigger we make this echo time, the stronger that percent change is. But we can't make this echo time too long because the signal is also decaying away with T2 star. So we have to pick somewhere not zero, not too long. And it turns out that the optimal echo time, TE, is typically on the order of the T2 star. Okay, so that turns out to be the optimal echo time. It's close to the T2 star. And that's around 50 milliseconds. Okay, at 3 Tesla. Okay, so let's talk a little bit about how R2 star depends on actually brain function. So when oxygen is carried into your brain or to all your tissue by the hemoglobin molecules, okay? And so when they're in your lungs, they pick up oxygen. So that's represented by these red things, okay? So this is oxygenated hemoglobin, okay, or oxyhemoglobin, HbO2. When they go into your tissue or in your brain, they give the oxygen off. for metabolism. And so underneath that, these blue things are iron atoms. Okay. And so as you know, iron is ferromagnetic, right? So this is going to tend to, and in this case, actually call it paramagnetic, but in this case, this is going to perturb the magnetic field. Okay? So the more iron there is exposed, the more the magnetic field will be perturbed, the more dephasing there should be. Okay, so if we look at a case where if we zoom in on this, not much iron is exposed, right? So there's some dephasing of the spins, okay? And now if we go here and we look here, almost all the iron has been exposed, so it's all blue. And so there's much more, whoops, sorry about that. There's much more dephasing of the spins, and so the signal is smaller. So the key to keep in mind is the more oxygen there, the more iron exposed, the more signal decay. The less iron exposed, less signal decay. All right. That's really the basis of fMRI. So let's see what determines how much iron there is, or how much deoxyhemoglobin there is. So more deoxyhemoglobin means more iron is exposed. Okay. So in your brain, there's really two competing things you have to think about. There's cerebral blood flow, which is bringing the oxygen, and there's cerebral metabolism, which is using up oxygen. Okay. And how much deoxyhemoglobin you have turns out to be the ratio of these two. So the more metabolism you have, that's going to tend to increase deoxyhemoglobin. So that's going to make the signal smaller. On the other hand, the more blood flow you have, the more oxygen you bring in. So that's going to tend to decrease the iron. And that would make the signal go bigger. Okay. So CBF increasing decreases deoxyhemoglobin. CMRO2 increasing increases deoxyhemoglobin. And decreasing deoxyhemoglobin will tend to make the MR signal increase. And an increase in deoxyhemoglobin will tend to make the MR signal decrease. Okay. So it turns out that in general, when the brain is active, we tend to see this increase in the MRI signal. So it means that overall, CVF is winning out over CMRO2. Okay. In fact, if we look at the ratio of the changes of the change in CBF, the percent change in CBF over the percent change in CMRO2, it's typically on the order of like 2 to 4. Okay, so that means that the brain, over many years of evolution, has been set up that it's going to give you more oxygen than you actually need. And it's going to do that at a ratio of like 2 to 4, depending on what part of the brain you're in. Okay. So this is a picture of what's going on. This is actually a graduate student of mine made this up for his PhD exam. So it's showing blood flow coming in and delivering oxygen, so oxyhemoglobin, and there's some deoxyhemoglobin here. Okay. And then let's say some neural activity begins, so there's some metabolism. So that's going to tend to increase the amount of deoxyhemoglobin. Okay. So that will tend to make the signal go down. And this is what's called the initial dip, which you can sometimes see, but it's very hard to see. It just happens very quickly and not always observed. But then what happens is pretty quickly, the brain's like, well, I actually need more oxygen. Okay, if you're going to start increasing metabolism and doing something, I'm going to start delivering more oxygen to you. Right? So that oxygen is going to outpace the rate of metabolism roughly by a factor of 2 to 1 or 3 to 1. And so that's going to deliver a lot more oxyhemoglobin. Okay. So the actual amount of deoxyhemoglobin there is going to decrease. And so that means the MR signal is going to go up. Okay. So that's the typical fMRI response that we see, is we see this increase in relation to MR activity. And then after the stimulation goes off, there's a return to baseline. And how that happens is still not quite known, but sometimes the signal does go below 0, and still there's some debate about what happens, why the brain goes below 0 here. But the main thing to remember here is that this is really what we're looking at, this positive bold signal And that's because CBF has increased much more than CMR2, such that deoxyhemoglobin content goes down. So actually we have about a minute. So actually let's do, these are pretty easy questions. So actually let's just do this just so you have, before your holiday, we'll have some questions to look at. So we can do these fairly quickly. Okay, so basically, let's see, where's decrease? Increase or decrease? Okay, so here's the first question. Does the magnitude of the bold signal percent change will increase or decrease as a function of echo time? Yeah, it's going to increase, right? Because it's, remember, we have minus delta R2 star times echo time. Okay, so the magnitude of the percent change will tend to increase, so that's good. We'll relaunch the poll. Okay, an increase in the functional CBF response, that's how much CBF increases in response to your stimulus, will tend to increase or decrease the bold signal. Increase, right? Because basically the more CBF there is, the more oxygen being delivered. So therefore the MR signal will tend to go up. Okay, that's good. Let's relaunch the poll. And then the final one is an increase in the functional CMR2 response will tend to increase or decrease the bold signal. Decrease, right? Okay, because the more metabolism, the more deoxyhemoglobin, the more dephasing, therefore the signal will tend to go down. Okay. So we'll look at this question on Monday, but I think this is a good place to end. So are there any questions about course logistics or what we covered today? Okay, so great. So on Monday, we'll finish up the fMRI and then we'll do a little bit of more advanced topics. And so next week will be more sort of advanced topics to get you up to sort of speed on the current state of fMRI as it's done these days. Okay. So I will stick around both online and in person for questions.